honors Algebra 2, Chapter 7, Section 3. So this is all about the number e. So number e is kind of like pi. It's a number we use a lot in math. So right here for this problem, we can kind of see where it comes from. Let's say you have an interest rate of 100% per year. Obviously, it's not going to happen like that, but let's say there is. Make it easy math for us. Compounded n times per year, where n is the allowed to vary. So compound, we're going to look at different times of compounding per year. So if we invest $1,000 into this account, so annually, we look at the annual compound annually. So here's our n value here. So this is our n value 1. So in our formula, 1,000 is our starting value. This is our 1 plus our percent. 100% will be 1 divided by our n value to the 1 times 1, because it's 1 year for 1 time per year. And if we actually evaluate that, we'd find a value of 2,000. So 100% increase. Now, the next one is quarterly. It's quarterly 4 times. So in this problem, the only thing that changes is that we have a denominator here of 4 quarterly, and we have this numerator here is 4. So if I evaluate that, we have $2,441.41. We have more because we're getting interest on the interest for that year, the 3 extra quarters. For the next one here, monthly, now we're going to do 12 times we're taking the interest. So we get more. Now if we do it daily, now we're taking interest every day, you calculate the interest. So you're getting interest on the interest daily, so you have more times. We get a little bit more money. Now let's do it hourly. So every hour, calculate that. A little bit more, almost $4 more. Let's do it every minute. So calculate it, so every hour, do it every minute for the entire year. So that's 525,600 minutes. And same kind of formula, you just change those two numbers and you get almost the exact same. Going from hourly to minute, you have an increase of 15 cents. Now, notice how this value doesn't keep increasing so much. Sooner or later, we're going to reach kind of a value or the same value. We're not going to have an increase in the amount. That is because this number right here, this quantity, is going to be approaching the same number. The only thing that's changing in these problems is our n value. Our n value is the number times compound. So if we're letting our n value become like larger and larger and larger, so if we let n become infinitely large, we are actually creating e. So e, this is all 7.3 is the number e. E is called the natural base e, or just e for short, but natural base e. The natural base e is an irrational number. So what does irrational mean? It means it's a decimal that doesn't repeat or terminate. Let's say stop. So it goes on forever and ever and ever and never repeats, like pi. Also square root of 2, square root of 3, square root of 5. There's many we've talked about. So as n, as our compounding, it approaches positive infinity. So as we let n get infinitely large, this quantity right here is going to approach our value of e, which ends up being 2.71828. So this is our value e. We treat e as a variable a lot of times, so we can use a lot of our exponent rules, like e to the second power times e to the fifth. We should realize that we add those, so we get e to the seventh. Here we need to kind of split this problem up into 2 parts. We have the coefficients, and then we have the powers. And so 12 divided by 3 is 4, and then we can subtract the 4 and 3 to get e to the first power. For the last one here, this 2 is a power of both the 5 and a power of the power e to the negative 3x. So we can just do that through. And then 5 squared is 25, and then we realize here we can multiply again. But we have a negative exponent. Now, I don't want to deal with negative exponents, we want to change it to positive, so we should make it a fraction. So using your exponent rules, they still apply to e. Just treat e as a variable. Using your calculator, we can evaluate some of these problems here. So e to the third, how do you punch it in the calculator? There's actually an e key. So you just find the e key, caret key to the third power equals, and test to see if you can do that on your calculator that you have, and you should get that value, 20.086. So these three problems here, you should roll through and see if can you calculate it without on the calculator correctly using your e key. And so these will be the values you have for these, and literally it is just punching it in the calculator, making sure you follow the order operations. So like some down here, this is e to the negative fifth, find that value first and then multiply by 9. And here e to the 1.8, find that value first and then multiply 6. So your calculator will do that, but make sure you're careful in your thought process using the order operations. So a function in the form y equals a times e to the rx is called a natural base exponential function. It's used a lot for growth and decay. So if a is greater than 0, r is greater than 0, then the function is exponentially growing. If a is greater than 0 and r is less than 0, then it's decay. So that r value is kind of like the rate at which the function is growing or decaying. So the graphs of the basic functions y equals e to the x and y equals e to the negative x are shown below. You can see how y equals e to the x is a growth and y equals e to the negative x is a decay value. And so these functions we'll look at more in the future, writing equations of these as well. So here we have the 2 is our a value, and then 0.5 is our r value. So it's talking about growth here. Now, just because it's a 0.5 doesn't mean it's decaying, or it's a little different. We're looking for e values that are less than 0 to state a decay value. So this is still going to be exponential growth even though we have that decimal value. And so if we look at our graph here, here's the shape of it. You notice that we have an a value of 2 here. We've not been moved left or right, but we have, here's an awesome a value here. So we go up 2. If I go right 1, you can see how the value 1, 2, 3 a little more, and that's where this rate is going to be taking effect. How fast it's going to be growing. A calculator is a good function to use, or a good tool to use when you start dealing with a natural number. For this one here, notice how we have +1, so that's going to shift the graph up 1. 1/2 that a value here, so it's going to vertically shrink it a little bit. But now we have our negative x here, so this makes it a decay. So I just have that thought process before I graph it, and I would graph it on a calculator. You can see how we're up, shifted up 1, so this is our horizontal asymptote is up 1. And then we have an a value here of 1. These are some properties I want you to pull from the equation before you graph it, but I would use a graphing calculator to help me graph it. And the last one here, this one now has an h value and a k value. 1.5 is our a value, 0.25 is our r value. So this is going to be growth. There's no negative exponent here, so x minus 1 just shifts it right. And so we know we have a down 2 is our horizontal asymptote. So down 2 here is be our horizontal asymptote. And then for down our a value, here's our a value going up 1.5. It's a little off there to get the shape of the graph. So here's where more problems, these are the more frequent problems we use with our natural number. The continuous compound interest formula is one you've probably heard of in the past. Some people call it PERT. So it's the amount of money equals our principal times e to our rate times t power. So the variables don't change, just kind of the setup. And so in this problem, we invest $1,500 at 7.5% annual interest compounded continuously, and that's the key word for 2 years. As soon as you see compound continuously, then you use the compound continuously formula. If we said compound quarterly, we're using the formula from the previous day. And so compound continuously, that wording tells me I have to use PERT. So in here, we're trying to find the amount of money we have. Our starting value is 1,500 times e to the r which is 0.075 for 2 years. When I punch this in a calculator, I have to make sure that I use parentheses for my power. I want to make sure that it does all that multiplication. And so if you do that, you should find the amount of money you get here is $1,742.75. That'd be compound continuously. And in real life, that's how our rates are found, compound continuously. So here's one more example, and I'll have this be your video problem to complete. And again, it says compound continuously, so make sure you use the same formula. We'll call that it good for the night. We'll see you tomorrow.